and I lead a very small group. So the main actor of the work I'll show you today are Daniela Amoroso and Paolo Barone. And yeah, I mean, I do, basically we do multifunctional material with density functional theory, as most of you. Actually, we work not so much on the method development, but we work mostly on understanding microscopic mechanism. And today I'll show you a kind of new microscopic mechanism in magnetism that's giving interesting physics. Okay, ferroics, I mean, probably most of you know what they are, but they are ferroelectric, ferromagnets, and ferroelastics. And a multiferroic is a material that shows a coexistence of at least two of these phenomena. So today, I'll get, on the limit of ferroic material in low dimension. There's a lot of interest in two-dimensional material, of course, as we've heard in the conference, and especially because you can change actually the properties in the monolayer compared to the parent bulk compounds. I'll focus on this part of the ferroic, so I'll basically tackle two-dimensional magnets. And when we'll think about two-dimensional magnet, the first thing that comes to your mind is probably the Riemann-Wagner theorem. So you cannot order a two-dimensional material if you have an isotropic spin. So if you have a isotropic spin Heisenberg model, there cannot be any long-range order. So it's very important to have a sort of anisotropy, right? And when you think about anisotropy, what is the driving force is spin-orbit coupling. So spin-orbit coupling is actually, usually for most of the materials we look at, it's kind of small interaction, but it gives rise to very rich physics, both in the magnetic realm and the non-magnetic solids. We have learned about topological matter and Rashba physics and spin-valley coupling and so on and so forth. But of course, it's basic in magnetism because all the application of magnetism actually relies on magnetic anisotropy. But it also gives rise to different microscopic mechanisms that are, especially the anisotropic exchange, were not so much explored, have not been so much explored so far. So two-dimensional magnet became very popular in the last 2 or 3 years, especially because chromium I3 was found to show a long-range order at a temperature of about 50 Kelvin. But we thought in the beginning, actually, we needed to understand a bit more about what was driving this order. So we actually started from a database in the group done by Nicola Marzari and his collaborator. So they were actually showing that there are several magnetic compounds. We wanted basically to have them ferromagnetic and semiconductor, so we focus on this region. And specifically, we focus on the nickel halide, nickel chloride, nickel bromide, and nickel iodide. So if you go back to the literature, actually not much is known, but something quite interesting is known. These were explored back in the 80s, and some of these show a very exotic magnetism in the bulk. So we thought, what happens if we now exfoliate a monolayer and look at the ordering of this nickel halide at the monolayer limit? So we do simple, standard VASP calculation with U and spin orbit, of course. So it's a kind of work in progress, especially because we have results, but not all of them are completely understood. So as I said, we have a monolayer of this nickel halide. So the coordination is an octahedral coordination, but these octahedra are edge shared. And the angle between nickel, halide nickel, is usually 90, it's very close to 90 degrees. So the tendency towards ferromagnetism, based on naive Goodenough-Kanamori rule, is supposed to be to point towards ferromagnetism. You have quite localized moment on nickel, and kind of positive and kind of sensible moment on the halide. Nickel is D8 to 2+. So you have semiconducting behavior. So the first ingredient that we need is frustration. Frustration is in the exchange. So simple, too simple and paradigmatic example of frustration is that if you have a spin chain and you have a first neighbor ferromagnetic coupling, but a second neighbor which is anti-ferromagnetic coupling, then you cannot satisfy all the interaction at the same time. So usually the ground state is non-collinear, and if the frustration satisfies certain limits, then the ground state is a spin spiral. The other paradigmatic example of frustration is the triangle. So you have an antiferromagnetic coupling on a simple triangle. So if you have like an antiferromagnetic coupling, these two spins would like to be anti-aligned, but then the third spin doesn't exactly know what to do, because of course if it satisfies one, doesn't satisfy the other. So the ground state is usually 120 degrees on the triangle, which sort of makes all of them quite happy. And you find them, all this frustration are generally in triangular lattice or Kagome or pylochrome lattice, which is a three-dimensional version of this. So frustration is very important to give rise to exotic magnetism and non-collinearity. This we knew, let's say. I mean, it's more standard. But we didn't quite know that actually the even exchange coupling at the first neighbor can give rise to non-collinearity. In which sense? In the following. So if I start from a general form of the magnetic coupling, so I have two spins, they interact with a matrix, let's say, a tensor form. It's a 3x3 matrix, and I can always decompose something which is isotropic, and then I can, by taking the trace of this matrix, and then I can take an antisymmetric term and a traceless symmetric term. So I can do that for every matrix. And so if I write it like this, then I go back to the, let's say, more usual form of the kind of spin Hamiltonian that we are used to see. So I have a Heisenberg term, which is a scalar product. Then I have a Tsiolkovsky-Moria, which is a vector product. And then I have this term, so an isotropic exchange, which is a symmetric traceless matrix. And so usually, what Heisenberg, of course, gives the relative orientation. Tsiolkovsky-Moria, because it's a vector product, tends to orient the spin at 90 degrees. This anisotropic exchange, what is usually doing is to orient the spin in a certain direction. So sometimes people call it two-site anisotropy. So it's an anisotropy, but it's an intersite anisotropy. So it's not usually the single ion anisotropy as we are used to think about anisotropy and driven by spin-orbit coupling. So already at the Moria back in the 60s knew very well actually that both these terms are actually important. The general argument by which this second term was somehow forgotten was that dm scale as z square and an isotropic exchange scales in the superexchange theory as z square. So usually spin orbit is small parameter, and therefore this term is dominating over an isotropic exchange. But in our case, we have a centrosymmetric system. So Tsiolkovsky-Moria is forbidden by symmetry, and therefore this term might become important. Also, due to the symmetry that we have, this is the form allowed. So we have three diagonal, in principle, different term, and then we have only one diagonal, off-diagonal term, which is, of course, the matrix is symmetric, so we only have one element to calculate. The other, let's say, method that we use a method that is somehow also new. This was proposed by Hongchun Shang at Fudan. It's basically called the four-state method. And basically, it's not different to what is usually done. So you always map, your total energy on a spin Hamiltonian. However, what you do here is you select, let's say, okay, I think I have a slide later on that better shows this. So let me show you here what you do basically, you select a couple, and then you calculate the exchange only for this couple. So in this case, this is the first neighbor, second neighbor, and third neighbor. So the way the four-state method works is the following. You fix a couple, and then you select different spin configuration. So for example, if you need to calculate jxy, as in this case, you have your spin 1 along x and spin 2 along y, but then they are embedded in the bath of spin, which are, let's say, ferromagnetic. And in this case, let's say, you're sort of achieving a higher numerical accuracy because you wash out all the other coupling to this bath. So you only isolate the intersite coupling between these two spin that you selected as a couple. And of course, here you need spin-orbit coupling, because otherwise this term wouldn't, wouldn't have any meaning. So what we have actually is this. So okay, here I have J1. Let's say I take first an approximation in which my matrix is isotropic, and then J2, and then J3. So the first thing you notice here is that, let's look, let's say, for nickel iodide. So you notice minus means ferromagnetic. So nickel iodide has a very strong ferromagnetic exchange, actually stronger than chloride and bromide. Then J2 doesn't matter, really very small, but then J3 is very strong and very positive. The fact that you have chlorine with a small J3 and iodide with a large J3 is consistent with the, let's say, the more ionic exchange coupling that you have in chloride compared to iodine. So iodide has 5p orbital, which are very wide, and they can mediate an exchange interaction in a wider scale. Chlorine is more localized, so it's meaningful that you get a J3, which is smaller in chloride than in iodide. But coming back to the J3, this is strongly positive, almost as big as J1. So actually, the first neighbor would like to be ferromagnetically coupled, but then J3, of course, makes a mess, right? Because due to the frustration, then this spin here doesn't exactly know what to do. So we expect some kind of non-collinearity. And this is, let's say, wasn't known, but let's say it was more standard. But what we didn't expect at all is the following, that if you calculate the exchange in a tensor form, so if you calculate an isotropic exchange for iodide, then you get a very large, like 20% of the, even larger of J1, let's say, and very strongly, let's say, even the diagonal term are quite different. This, of course, happens in iodide, and not in chlorine, so it's related to the, let's say, spin-orbit coupling of the anion, not of the nickel itself, which is consistent, let's say, with the fact that here you're examining the effect of spin-orbit in the intersite coupling, not on the single ion anisotropy. So it's a sock of the ligand that is really important. So what is kind of exotic is that you have a strong anisotropic exchange, very strong. And then we also calculated the single ion anisotropy. So one word of caution, of course, since single ion anisotropy gives usual anisotropy, but this anisotropic exchange is also giving an anisotropy. So the magnetic anisotropy energy is actually the sum of the two, of the single ion plus this anisotropic exchange. This has to be, kept in mind. So then with this parameter, then we did Monte Carlo simulation for all the three compounds. And okay, for nickel bromide, what you get is this, so which you sort of expected. So this means that you have a helical structure. So here, okay, what I show here in the plane, this arrow mean the XY component of the spin, and then the color scale means this SZ. So for example, if you look at this part here, these are spin. This is 24 by 24 spin. So you see a cycloid running like this. And then at the same time, the Z component is also changing. So it goes from negative to 0 to positive to 0 to negative and so on and so forth. So you have some exotic magnetism even in nickel bromide. You can zoom it in to understand better. In chloride, basically the spin orbit is 0, right? So you don't have any source of anisotropy. And in fact, it doesn't order. If you calculate specifically, it's basically flat. Or it orders, I mean, it's not completely forbidden. In principle, it could order because of frustration. But it's, let's say, we don't see a clear sign of ordering. Whereas in nickel bromide, you really see a very strong transition. Temperatures are quite low, of course, 20, 30 Kelvin. But surprises came from nickel I2. So, of course, this is very different from nickel bromide. You see some kind of spot here. I think I have a zoom, which is something that we didn't expect at all. And maybe some of you are familiar with skyrmion or some localized object, like localized spin texture. So I went back to some slides stolen to Stefan Blugel, who's the main top player in DFT for skyrmion. So what is a skyrmion, actually? Skyrmion is a particle-like nanometer-sized spin texture of topological origin. So it can have different hardness. For example, if you go to the center of the skyrmion to the outside of the skyrmion, so you go from down to up, then you can rotate clockwise or counterclockwise, and this gives the so-called handedness or rotational sense. And also you can map, this two-dimensional spin texture on a sphere. And typically all these skyrmion, systems show a phase diagram which is usually like this. So you have a helical structure. You start from a non-collinear structure. Then if you apply the magnetic field, then at some point at a certain temperature, you cross the skyrmion phase. But this you usually achieve with magnetic field. Usually skyrmion is not a ground state. And there is a zoo of skyrmion with all kinds of spin patterns. And actually, also in addition to having right-handed or left-handed skyrmion, you can also have anti-skyrmion. An anti-skyrmion is something where the rotational sense changes as a function of direction. So, for example, here is going like this, but then in this direction is going the other way around, like this. So the rotational sense changes from direction to direction. And you can even have this complex object where the rotational sense changes every 60 degrees. These are called anti-skyrmion with higher order anti-skyrmion. So skyrmion are actually topological objects and are usually characterized by this topological charge, which in a continuum approximation is calculated in this way. Of course, we don't have a continuum model, so we have to discretize the system. And we calculated basically the topological charge is actually boils down to calculate the scalar spin chirality, so a triple scalar product. So you have two spin, you make a vector product, and then you scalar multiply by the first spin. So actually, if you calculate this topological charge, it's actually giving you a measure of how many times it wraps, the magnetization wraps around a unit sphere. So if you do this mapping, actually how many times, in this case 1, the spin texture mapped onto a sphere encloses, let's say, the center. So we calculated, because we are also kind of new in the skyrmion field, so we calculated the topological charge, and we got actually Q equal 2. So we went back to Stefan's paper, and we actually observe, actually looking better at what our spin texture, it's actually really close to what they observe. However, they observe it under magnetic field, and also the origin is different because all the skyrmion in the skyrmion community are actually or not all, let's say, but generally they are driven by Zelowski-Moria. But here we don't have it, so it must be driven by something else. Frustration certainly matters, but it cannot be the only source, because in nickel bromide, I don't have the Q equal to. So if I calculate the topological charge for nickel bromide, I have 0. So the only one giving, a topological charge different from 0 is nickel iodide. And so it's a topological ground state. No B is needed here. As a first example in two-dimensional magnet, at least to my knowledge, is not driven by Zelowski-Moria. Also, we see a skyrmion lattice, which seems to be commensurate with what we see. It's like 8 times 8, although we are in the process of calculating the Fourier transform of the spin texture so that we can be more precise. But it really seems a skyrmion lattice. So what happens under magnetic field is the other question. So if I now apply in a Monte Carlo approach, if I add a Zeeman term, what happens? So the nickel I2 actually transform now into a more conventional skyrmion pattern. This is, let's say, more conventional. So actually, if I now plot the topological charge as a function of my magnetic field, then I can identify a first region in which I have this anti-skyrmion pattern up to 30 Tesla. So this, state is really strong. You cannot destroy with a magnetic field. It's really robust, and it actually doesn't change. For example, with U or J, or if you strain it. So it's really, really strong. And then there is a region in which you have more like a conventional skyrmion light, and then of course, it goes ferromagnetic if you apply 120 Tesla. And these transitions are really sharp, so it's really kind of, changing topology. So we're, say, still investigating the origin, but we really think that anisotropic exchange is making the game. So actually, if I have a symmetric matrix, I can always diagonalize it. And if I diagonalize it, I can get eigenvalues and eigenvectors. So I can draw my eigenvectors on the kind of real coordination, real lattice. So if I do that, 2 of the eigenvectors lie in a plaquette, let's say identified by nickel iodine. So the plaquette are somehow, if this is the layer, the plaquette are somehow bent in a triangular shape. So one eigenvector is oriented along nickel-nickel. The other one is oriented more or less around iodine, and the third one is, of course, perpendicular. But then you have 3 plaquettes. So the arrangement is such that you have 3 plaquettes. So actually, the eigenvector actually point into, they drive basically, they are going towards, the center of a triangle, which gives not only non-collinearity, but non-coplanarity. Of course, to have a spin chirality, you need non-coplanarity. And we really believe that this is the source of, kind of non-coplanarity that then gives rise to the topological charge. So the question is, can one have similar thing in chromium I3? Because, the ingredients are what? The ingredients are spin-orbit coupling, which you have, strong in chromium I3, as strong as in nickel I2. And then we believe also that frustration is somehow needed. So if you only anisotropic exchange, then it's probably not enough to have such an exotic magnetism. And actually, people calculated the anisotropic exchange for chromium I3 in Hongjun Zhang group. And also, the J1, J2, J3 were calculated in another paper. However, the fact that you have a honeycomb lattice. So it means that there's a hole, in between the chromium. So you have some anisotropic exchange, which is a little bit smaller than what we have, but especially you don't have frustration, because the J3 is basically 0, because it cannot be mediated by we have an ion here. if I now compare with nickel iodide, this is a triangular lattice, so it means that there's no hole. So the fact that there's no hole actually gives rise to a big J3. This is a sign problem here. This should be positive. However, J3 can be positive also if you have a triangular net. We don't think it can be positive here because there's nothing to mediate that. This is actually probably one of the reasons why chromium I3 is ferromagnetic, and nickel I2 we don't know because there's no experimental result. But we really believe that the exotic magnetism is there, and it would be great to have a confirmation from experiment. So let me conclude. So we found exotic, very topological state of matter as a ground state, no B field needed, is not driven by DM, but by a combination of frustration and an isotropic exchange. And we have also a very peculiar behavior as a function of the magnetic field. So with this, I would like to thank you for your attention, and I'm ready to answer any question you might have.
Thank you very much, Silvia.
Thank you for your great talk. I have two questions.
Yeah,
the
please.
first one is that in your Monte Carlo simulation, you have commensurate or finite number of skyrmions in your unit cell. So what happens if you increase your supercell gradually?
Laterally, so it's scale, the Q, it's scale as a number of skyrmion. So we calculated, so it means that, let's say, this Q2 is per skyrmion. So if I have, let's say, 24, then I have, let's say, my Q is Q times this object. And if I now have 32, let's say I have more skyrmion, then my total charge would be, let's say, multiplied, commensurate by the size of the skyrmion. The size of the lattice, sorry. So it really, let's say, is related to the number of objects I see, let's say.
Sorry, my question was,
You want me to put back your...
No.
So let's say if I put now 8 more spin, this is what you're asking?
No, actually, if you slightly increase your supercell, not...
Okay. Let's say you don't make it commensurate with 8.
Right, or my question is that, is there some characteristic length scale of the skyrmion?
That's a good question because, let's say it's both related, so in DM it's typically D over J. Here we have 2 ingredients because there are 2 scales. So J3 over J1 is probably something, and then JZY over J1 is the other scale. So if we are doing some other simulation, tuning, let's say, artificially the parameter, and for example, if you reduce the frustration, this skyrmion get a little bit bigger. This is certainly the size is related to the, but we don't have, let's say, a complete phase diagram, let's say, of all the JZ, Y, and J3 over J1. But certainly the scale, the radius, let's say, of the skyrmion is related to both. Because, of course, if I don't have JZY, if I don't have any anisotropic exchange, then I don't even get a skyrmion. So in nickel bromide, there's no skyrmion. So everything is topologically trivial. So it must be related to both. But yeah, I don't have, something very clear would probably, be shown by the, if it's really commensurate, would be shown by the Fourier transform, which we are doing currently.
Okay, thank you. My second question is
Yes.
that, have you considered your findings in terms of Kitaev spin model?
So, okay, Kitaev could be, let's say, if I diagonalize it, then, my eigenvector would be oriented in the plaquette. So if I, let's say, consider as a Kitaev basis the plaquette, then I get 2 eigenvalues are indeed quite close. The third one is a bit different. So let's say in this sense, you can force it to be a Kitaev. So you can make, 2 two of them to be exactly equal and one of them to be different. Yeah, you can, let's say, force it to be. It's like maybe 10% the difference of so I don't have two eigenvalues and then a third one which is different. I have two quite close and a third one which is different. So in this sense, yeah, it's the closest thing I can think of is Kitaev, but it's not only Kitaev. It's not full Kitaev.
Because people are excited about Kitaev model. Maybe
Right.
you're
Sure. So in Chromium I3, for example, the anisotropic exchanger were actually discussed and made a connection with Kitaev. Is the Kitaev not in the XYZ, but is in this different, let's say, spin vector basis.
Thank you very much.
Yeah.
So very interesting results. This is a spin-2 system, right? So you are in a spin-2 system. Now, my question is, first of all, when you extract your parameters, and you were mentioning that the spin-orbit coupling maybe of the iodine or bromine may play a role. So with that, you are assuming that probably the hybridization plays a role.
Oh yeah.
Because otherwise you cannot get that. And the second question is about Kitaev. You don't have bond-dependent type of interactions, right? Because here you are, and the way you define this, it's a spin-2. Your operators are, your spin operators is a spin-2. It's not spin 1/2.
Right. So in this, in fact, I said, I can, let's say, interpret in a Kitaev sense if I consider like J isotropic plus K. Okay. In this sense, I can map into a Kitaev. Then, of course, he's a spin-2, yes. So, let's say, in this sense, it's kind of different. Hybridization is certain. It's an intersite. It's an intersite coupling. So it must go through the iodine. So iodine must be very important. And this is also why we don't see, we don't see anything important or relevant in chlorine, right? So iodine really makes the game.
My last question, how much do you trust this way of extracting the coupling parameters? Because of course your results depend extremely on that. So how much do you trust this method?
So
have you checked it with
what do you mean? For spin fluctuation or for
for
parameter?
For obtaining your JXY.
This is I come from oxide, so I'm usually I'm used to seeing crazy behavior as a function of U and J. In this case, it's quite the sensitivity is small. And even if you make, your Monte Carlo simulation with different parameters, this state is really strong, probably too strong. So even if you apply 120 Tesla in the plane, you really see like a spin texture, which is very much topological. Of course, out of plane, eventually they go up. But it's very strong.
Okay, thank you for a very interesting talk. So you obtained a very large value for J3 for nickel iodide.
Sorry?
You obtained a very large value for J3, the third nearest neighbor exchange.
Yes.
And so this contributes to the frustration in these systems. So did you check J4, J5? And
yeah, we did. Not with the four-state method, because four-state method means that you isolate a couple and then all around so they must be ferromagnetic, right? So if you have J5, this means that they are very far, and then we couldn't, really build a very big unit cell in the four-state method. But you really need four-state method if you have like JXY. I need four-state method, but J3 is very much isotropic, and J5 we didn't check that, but we expect it to be isotropic. And we mapped actually on, simple Heisenberg using J4 is really 0. J5 is basically, the mapping that you get is, basically 0. We consider it to be irrelevant, let's say.
Very short question about this beautiful skirming pattern. Currently, what is our knowledge about the experiment knowledge about this material?
So people don't like iodide apparently is very it likes to attract humidity. So we are trying to convince, but I think somebody told me that they tried not nickel iodide, but vanadium iodide, and the flakes disappear or degraded. So probably one needs kind of protection for the iodide. But not much is known. I mean, there are these old paper for the bulk and nothing more recent. These were back in the 80s, and nobody tried to exfoliate.
So I'd like to make a question related to what was asked before about the calculation of the J's.
Yes.
And in connection with the DFT plus U, because we're using DFT plus U with a spin orbit. There is a recent paper by Nicholas Spalding saying that when you have both things, you have to be very careful on how to use to choose U and J.
J, yes.
Otherwise, things can go very.
Yes. So we use the Liechtenstein approach, and we try to change both. I'm aware of the paper you mentioned, and actually in some other case, as I said, this system is not really sensitive. But of course, when you have spin orbit coupling, then J is very
So
Hun's J is very relevant. We try to change it. Let's say, not but we try to change it. Let's say from 0.6 to 1.3. Let's say in this energy range, and also the U. Let's say from 0 to 4, I think. Okay. So we didn't go to extremely high value, but we didn't, as I said. I mean, the J's are very solid, and always you see strong ferromagnetic J1 and strong anti-ferro J3, always.
Very nice. This is easily exfoliable, so the binding energy is small. So it could be that also the 3D parent might have the same magnetic state or texture. And then it would be very interesting because, like the triangular antiferromagnetic easing has this very weird specific heat. So one could actually do measurements of the specific heat of this system.
Right. Yeah, we wanted to, actually we plan to do, we want to do several things, but one thing of course is doing, bi-layer, tri-layer, and then, going up to the bulk. I'm a bit, I think I'm not completely sure that DFT is describing, exchange coupling within this van der Waals gap. I didn't think, maybe we are fine, but, these are small energies, and I don't know if somebody has really looked into the, predictability of DFT for this interplanar exchange coupling.
There is a spin van der Waals extension, no, by the.
But for spin exchange, okay. And then of course so let's say this would go into the direction you're mentioning for going towards the bulk. The other thing, of course, is applying an electric field and CDM. because DM is 0 here by symmetry, but how, for example, if you also have some kind of, let's say if you drive the non-symmetry, how the DM grows compared to the anisotropic exchange term. This is kind of interesting and nice.
So one last question.
Just regarding your Monte Carlo simulations, so what's the temperature you do the simulations then?
Well, the temperature here, let's say, the Curie temperature, or Nel, or Skirmionel, I don't know how to call it, but it's like 40, 50 Kelvin, the Curie temperature. And the snapshot here are like 3 Kelvin, so that the snapshot I'm showing, these are really low temperature. But the Curie I don't think you can expect, very high temperature with this large frustration. I don't think we can go up to, of course, J1 is really strong, quite strong because it's nickel. But then you have a lot of competing mechanism that will, bring down your transition temperature.
Okay, so thank you very much, Silvia. So unless there is any